Hello all. So I just wanted to go through a couple more examples with you dealing with drawing force diagrams and how they can and should look. We'll also go into the functional forms of some of the forces. Some you have to calculate and some you have to use a relationship that has been determined and known. So we have our first example here. We have a skater moving at a constant speed across frictionless ice. So as we were doing in class the other day, first general strategy is to draw a circle around the object itself. We then want to identify any place in which our object, which is the skater, is contacting with anything else. And that seems to be only happening in one place, which is where the skates are touching the ice. So for that point, there would need to be a normal force acting upward. That normal force is being done on the ice to the skater. And that's the only contact. Sometimes when we have contact between a surface, there is friction parallel to the surface of that object. But since the skater is traveling with a constant speed on frictionless ice, there are no horizontal forces. And then, right, the earth is below the skater, and so there must also be an F-grav acting on the person from the earth. So from the earth on the skater. And that's all of the forces that are here. We just have a normal force from the ice and then the F-grav from the earth. Those two are going in opposite directions. And since the skater isn't burrowing into the ice or jumping off the ice, both of these forces should balance and be equal. And we can denote that stealing a tool from geometry. When you have two things that are equivalent, you use these little hash marks. So to clarify that the F normal is equal to the grav, that's what these little hash marks are for. Okay, so that would be the force diagram or free body diagram for a skater moving at a constant speed across frictionless ice. The next example that we have is a softball player who is slowing as she slides into the base. So our object of interest is our softball player. If we're identifying places that are in contact with other things, she is touching the ground. That becomes indicative of the normal force acting upward. So an F normal from the ground on the player. Okay, since we have our softball player is slowing, then there's something that's impeding the motion. She looks to be traveling to the right, but she's slowing down. So that means that the frictional force that is present needs to oppose the motion. And so your frictional force should be going off to the left. With frictional forces from the ground, and it's acting on the player. Okay, that's the only place that she's in contact with anything, but we are still missing one force. The earth is below her, which means that we need to have an F-grav from the earth acting on the player. So just a reminder, right, these subscripts that are here, the first one is the type of force, the second is who is doing the force, and then the last is the object itself. So for a softball player slowing as she slides into a base, she has three forces: a normal force from the ground, F gravity from the earth, and a frictional force in the opposite direction of motion from the ground. If we're talking about forces that are balanced, the only ones that are balanced are the F norm and the F grav, because again, she's not digging into the earth or jumping off the earth. She's staying right at the same level as the earth. So this would be your force diagram for a softball player who's slowing as she slides into base. Okay, so this next example, we're not going to do too many spring problems in this earlier part of the class, but we will come back and study springs in a great deal of detail. So in this case, we're really drawing a force diagram for the block. And if we were to consider all the things that are touching the block, we have a spring. And that spring is pulling on the block in the upward direction. So this is a spring force from the spring acting on the block. And that's the only thing that's actually touching the block. But presumably the earth is somewhere down here below that block. And so we should also have an F grav from the earth on the block. Just based from the picture, it's a little hard to clearly establish relative lengths of these two forces. If this was simply hung and let to sit, then you could easily make an argument that these two forces are balanced. Otherwise, it really depends on whether or not the spring was pulled down below its equilibrium position, in which case your F spring would end up being greater than your F grav, because that would be the only way to explain why the spring wants to return in the upward direction. Or you could also compress the spring, in which case your F grav would end up being greater than your F spring, and that would be the only way to explain why the block would begin to accelerate if allowed to stretch the spring again. Okay, so these higher level cases we'll really save for when we talk about oscillations later in the quarter. So for this block, just two forces, F spring and F gravity, and if it's simply sitting there static, then those two forces should balance. Okay, this last one's kind of an interesting one. We have a nail that's being picked up by a magnet, and in this case, the nail is really the object of interest. So if we circle that, we can still keep going through our same little spiel. We're interested in anything that's actually touching the nail. You have a magnet that's touching the nail. So there's actually two pieces there that become important. There's actual contact between the nail and the magnet, which means that there should be a normal force. And this will be a little weird because it's actually that normal force is going down. It's from the magnet on the nail. But more importantly, since it's a magnet, there is an attractive force, a magnetic force from the magnet on the nail, and that's pulling the nail up. It's bringing it to the magnet. When we're dealing with magnets, if we have a magnet and some material that's attracted to magnets, right, that's always an attractive force. If the nail was like another magnet, and it was the north end of, right, if the top of this nail was the north end of a magnetic nail, right, it would be repulsive. But since it's just a regular old nail, and so it's just going to be attractive. And then the last piece would be presumably the earth is down here at the bottom. Oh my goodness. The earth is down there at the bottom, so you would also have an E, a force due to gravity